Hello, in this week, we are going to understand an internal mechanism provided by ARM, that is interrupt handling. So you may find a reference reading in the textbook from sections 9.1 to 9.4 is about the concepts related to synchronization and why interrupt can handle the synchronization. And then specifically as learning outcomes, we are going to see two types of interrupt handling. One is about edge-triggered interrupts. You may relate this to keyboard. And another one is the cyclic periodic interrupts. So they are found in sections 9.5 and 9.6. And today we are going to look at the concepts of interrupts and synchronization as well as the cyclic periodic interrupts. To understand why we need interrupt handling, let's first look at the diagram of the hardware. We have our ARM as the CPU, and we have also learned that our CPU could interface with many hardware. We have talked about the switches that is interface on GPIO, so I use an arrow connecting to ARM, meaning that we have a hardware GPIO interface to the ARM. Similarly, we can have keyboard, that is the external keyboard, which is also able to be interfaced with the ARM. Now we have display, LCD, and you can have to get the communication module to play with Internet of Things, and so on and so forth. Some of these are input hardware, like the switches and keyboard. Some of them are outputs, like the LCD display, and some are both the input and the output, like the communication module. So what's the problem of using this hardware? The hardware actually acts much slower than the software. Remember that you have to write device drivers to configure the hardware to work properly. And the device driver also includes reading and sending data to the hardware. Now, because the hardware works slower than the software, here is an issue of hardware and the software synchronization. To be specific, when we say synchronization, it means when your software expects to get some data, say you expect to get some readings from the switches, you may recall in your labs you use a while loop. The while loop has a condition decision making. The decision making is about whether the data register related to the bits of the switches has data or not. That is called software waiting for hardware, because you have no idea in advance when the users is going to press the switches. And similarly for the keyboard, you have no idea when your user press the keys. That's why there is a waste of time on the software side. It just waits there, implemented in the while loop or a fixed amount of time, doing nothing, just wait for inputs from the hardware. So to improve the performance, we would like to shorten the time of waiting on the hardware. That's because if you even spend 1 millisecond waiting for the inputs from the hardware, 1 millisecond is hundreds of times of our clock cycle, the 62.5 nanosecond. So within that 1 millisecond, you have multiples of nanoseconds pass away, which means you can actually execute many lines of instructions. So we are wasting time. That's why we need to improve the performance. But by how? This is why we need interrupts. It can help us to do something while the data from the hardware is not ready. So this is a topic about the internal mechanism on ARM that could nicely solve the problem of the hardware and the software synchronization. Now, before we get into the interrupts, let's see through one example to understand the improvement performance through interrupt. So here is 3 flowcharts. I use the lines to separate them just to say, okay, there are 3 scenarios. The leftmost side, you see the 4 steps. You can imagine that they are 4 functions doing some data processing one by one sequentially. Now, suppose we have to get some data from hardware before we can do step number 2, this function here. Then the old way of busy wait, say you are doing a while loop, is to just stop after step 1. The stop is going through a while loop the while loop waits for the readiness of the hardware inputs or data. So it goes like this decision making, on and on. If the decision tells making tells us, oh no ready, then we still go back and wait for the next round. Only if it's ready, then you move ahead to process the data in step number 2, and so on and so forth. That's why we say this type of waiting through a while loop, it's a busy waiting, and it's wasting time for your software resources. Now, as a recall, how does your software and hardware know each other's status? You may recall the registers in the past lectures and the labs. Registers has a few bits. Some of the bits tell the information whether the hardware is ready or not. So those bits are called flags. Therefore, actually, your while loop here, the busy wait part here, is to decide whether the flags tells us the data is ready or not. So flags is a way to interface the hardware and the software. Now let's move on to the right part. This is a way of the interrupt handling. We again start from the step number 1, the first function, and then we understood that after step number 1, in order to execute step number 2, 3, 4, we need some data from the hardware, but it's not ready yet because of the delay on the hardware side. So what actually we can do is to set up interrupt handling. And after step 1, we immediately switch to run another task. I denoted as task here, and the first step is denoted as T1, next step is T2 and T3. So this new task does not depend on hardware data. So there's no sense to wait for data anymore. You just switch from step 1 to another task and running it. Now, when the data from the hardware is actually available and ready, then you stop the running on the task here. We don't know which step you stop it, maybe inside T1, maybe during running T2, or maybe inside the T3, we don't know. But what we know is that we have an interrupt handling set up, and whenever the data is ready, you stop running the task and switch to run the previous job of 3 functions denoted as steps 2, 3, 4. So in summary, when your data is ready, you switch to run the interrupt handling code written down on the right side. You may notice that there are no arrows pointing to either from the left to the right or the right to the left. That's exactly because we don't know in advance at what moment the interrupt is going to run, but we do know while waiting for the interrupt to happen, we can do some other task. So this improves the performance. Our microprocessor is never lazy, and it's always doing something. So we are going to introduce the concept of interrupts, how we are going to set up interrupts, and through the example of SysTick to understand a use case of interrupt handling.